Okay, so this is the last part of our first section of the school year, end of section 4.1, and we're going to learn about another type of sampling technique in this section. So, the new type of technique is called a cluster sample. And let me go ahead before you guys get lost in reading my definition and everything and walk you through a little hypothetical example. Let's say I had a big apartment complex with a lot of units in it. So it's like a lot of separate buildings going on. So I've got all these little buildings in my apartment complex right here. And I want to know what residents think about raising the rent a little bit to build a new pool. So I want to build a super cool swimming pool right here, and everybody's going to love it. It's going to be great, but I got to raise rent a little bit to be able to buy the pool. So I could go and talk to every single resident, and if I didn't own that many buildings, that probably honestly is the most fair thing to do. But let's say it's just a big complex and I don't have that kind of time, so I'm just going to take a random sample instead. I could do an SRS, just number off every person who's paying rent to me and then choose randomly that way, and that would be great. I could also do some sort of a stratified sample. A good variable to stratify by might be income. If somebody has a lot of income, maybe they're willing to have a pool put in where if they're not making as much, that may not be something that's worth the expense for them. So if I somehow had access to their income levels, I could stratify by that, get people in the high income group, medium, low, whatever, and pick some from each group. And that would be fine. A lot of times stratified samples, though, are more difficult to execute compared to other sampling techniques. So let's say I did do that by income, I might have to go over to this apartment, talk to that floor right there, then go all the way over to here, and then go to there and go to there, and get all these different apartments. The same thing would actually also happen in SRS. I'd be running all over my complex talking to these different people. So they introduce another valid sampling technique called a cluster sample instead. And what a cluster sample does is it breaks population up. The population is all my apartments, residents here. It breaks them up into groups that are called clusters based on proximity or something that's already pre-established. So for example, in my apartment complex, each building is a nice little cluster already. There are already a bunch of people in here, a bunch of people in here, a bunch of people in here, and I can treat these like my separate units in my problem. Now, cluster sampling says that what you do is instead of numbering off people, you're not going to number off every single apartment in there. You just do the building itself. That's building 1, building 2, building 3, building 4, etc. And you randomly choose your numbers. So you're going to choose, I chose number 3, number 7, number 11. Those are my buildings. So what I would do once I get my numbers is I would go and I would use everybody in that building for my sample. Everybody in that building for my sample. In a stratified sample, I take a little bit out of each separate group. In a cluster sample, the randomness happens from picking the groups themselves. But once I have my groups, I use everybody inside of that group. This can be a good thing. Cluster sampling is good in the sense that it's easier. People are already in buildings. If I own this giant complex, I don't have to run around everywhere. I just go to the buildings that I chose and use those people. It doesn't work out very well, though, if the buildings are different in some fashion. So cluster sampling kind of assumes that this building is the same as this building, is the same as this building. One building is as good as any other. Basically, in order for this to work well, your clusters need to represent mini populations. So in order for this to be effective, clusters should be mini populations. Okay, so let's talk about some ways that my little apartment example wouldn't be so great. What if I had a bunch of fancier apartments, like luxury apartments, in one of the buildings? Like, say, building number 1 was really fancy apartments, and I chose that building for my sample. Well, if this building is different than the other ones, those people will think differently, and that's not good. I'm going to get bias in my results, or possibly, or certainly increased variability between different samples. So if you have buildings that are different, it won't work out so great. Every building is supposed to be about the same. If I would have thought that, oh, each building is different, I could pick some from each and do a stratified sample. So cluster sampling works if the buildings are more or less similar to one another. Why do we do it? I've already talked about this. It's usually more efficient and easier to execute compared to a stratified sample. It's easier to walk into one building and talk to everybody than it is to run around and do a little bit of each. Keeping these two techniques straight is going to be really important for you guys. So I have a little thing that I use, little phrase I want you guys to write down. So stratified versus cluster. So a stratified sample is going to be similar within and then difference between. And my example of that was my freshmen, my sophomores, my juniors, my seniors. With you, I don't know why I wrote R there. SR, that's senior. Each bubble, freshmen probably feel about the same as sophomores feel about the same, juniors feel about the same as each other. So all juniors think somewhat similarly about the prom thing, but juniors compared to freshmen probably have different opinions. So the bubbles themselves are very different, but within the bubble, you're saying they're more or less the same. A cluster is going to be the opposite of that. So clusters are different within. You're going to get people from all walks of life within. So in the apartment building, you'll have some people with higher income, some with lower, presumably, but they're similar between. Both of these are valid, good sampling techniques that are, if used correctly, can be better than an SRS, but they take thoughts to execute properly. If you do a bad job thinking through either of these techniques, it's not going to work out for you. So I have a big example to talk through the different techniques here, and we're looking at a library. This library is really big. It has 20,000 books in it, and for some reason, this library isn't organized by section, like by type of book. It's just A through Z. So we got like big old shelves with the books starting with authors A all the way through Z. First thing they ask us to do is to just like describe in detail how you would do an SRS. And I have these written out. So I want to talk you through this, but you can ultimately just write what I have right here. You can make a little paragraph like I did, or you can do like a list, boom, 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 like that. It's up to you either way. You can abbreviate, you can do whatever. But there are problems that ask you to talk in detail about what you're going to do. Kids tend to find these a little bit annoying because you have to write a lot and you have to be fairly specific. But in general, when they ask how to explain a sample, you need to make sure that you are going to be super detailed. So explain how to select a simple random sample. Detail is going to be so key in this class. If there's one thing I write for you on feedback again and again and again over the course of the year, it's going to be detail. You need to make sure you're being very specific in how you do things. So talking through my library, I have 20,000 books. The first thing I should do is I should label each book and give them a number. So you can see right here that I said assign each book a unique number from 1 to 20,000. That word unique is key in this problem. It's kind of like a stupid thing, but like if I just say, oh, give everybody a number from 1 to 20,000, what if they use numbers repeatedly? Oh, that's 1, that's 1, that's 1. By adding in the word unique, you're making sure they're not being like ridiculous in how they are setting up their labels right here. So the first thing you do when you're asked to write one of these problems is you talk about labels. And you need to make sure you specify they're unique. Then you need to talk about how to get your random numbers. It says rand numbers right there. So I'm going to use a calculator. I'm going to use the command randint 1, 20,000, and I'm going to select 500 unique numbers. Again, I use the word unique. It's a great word for this because it means you don't repeat things. But even so, you need to be very explicit, and I just go ahead and say reject repeats or throw out repeated numbers. So you also need, when you do one of these problems, to talk about what happens to repeats. And I don't want to repeat a book when I'm making my sample. And finally, you're going to talk about what you would actually do, your action. I am going to look at the number of pages in each book. So writing these out, to be specific enough, you have to do these 4 things. It's kind of a lot and it's a little bit annoying to write it out. I sympathize with you there. I don't super love writing them in detail, but the AP test will do this to make sure you truly understand what it takes to collect random data. All right. So second thing is a stratified sample. In a stratified sample in this same context, you would have to think about a variable that matters. What makes a difference in how long a book is? And one thing that they kind of fed you in the problem there was they mentioned the word genre and put that in your head. It seems plausible to me, like think about like a comic book or a magazine, that type of genre is going to have a different amount, or even like a little young adult fiction novel compared to a big history textbook or a big encyclopedia or something like that. So the type of book presumably makes a difference in how many pages it has. So what I could do then, instead of one big list, I would take all my history books, number them off to 1 to whatever, all my fiction books, 1 to whatever, all my, I don't know, whatever kind of books there are, and I would pick some randomly out of each group. Now, when you do a stratified sample, you don't always have to do the same amounts in each group. Let's say when I'm doing this problem, I have like, I don't know, tons and tons of fiction books, but my little encyclopedia pile is actually smaller. You can pick them with like in proportion to the actual population. Like let's say, for example, 50% of the books in this library are fiction and only 10% are encyclopedias. I could make it so 10% of my sample is encyclopedias and 50% is fiction. So you can pick with respect to the population, and that's totally cool. But in this problem, a good variable to stratify by would probably be the genre. Other things kids have thrown my way over the years, where they are on the shelves. Presumably, you're not putting giant, massive things like this way on the top shelf because it's going to hit somebody in the head. So somebody said, couldn't you do like the bottom shelf as one strata and then the next shelf and then the next shelf? That's a possibility too. There's a lot of things you could do to stratify by a genre. It was just the first, most obvious thing I could think of. So let's keep it going then and talk about the same scenario with a cluster sample. The books are set up on shelves of 50. And the way that I made my library is maybe unrealistic because I said my library is just straight up alphabetical, not separated into genre like most libraries are. If it's straight up alphabetical, each shelf is probably one about as good as the other. That's not how most libraries are. Like if I had all my encyclopedias over here, a cluster sample would be a bad thing because this is not the same as this. But assuming that, oh yeah, they are all about the same, if the shelves are similar, then all I would do is I would number off my shelves, 1, 2, 3, 4, etc. I would do a random sample and pick my shelves. And then once I got my shelves, I would talk to or look at every book in that shelf. So that's how you could incorporate a cluster sample. So what is a drawback to each method? Talking specifically, I want to focus on the SRS is fine. SRS works well, but the SRS and the stratified in my library are making me run all over the place to go find all those books. This cluster is going to be the easiest of the 3 to execute because I can just go to one shelf and sit there and like look at all of those books. So the cluster frequently going to be more efficient, still works well if the clusters are legit. But if the bookshelves actually are different and I'm making a bad assumption, I can get bad data that way. So let's move on then and talk about this slide. So this is a new context right here. Now we're looking at kids at a university, and we want to know what percent of students were at class every single day. So what percent of students didn't skip any of their classes? And the only difference between these 2 pictures, each dot is going to be like a separate sample. So it doesn't say, oh yes, it does. It says I'm talking to 100 people or I'm talking to 400 people. So what this means, because this is honestly, this simulation stuff right here is one of the hardest parts of all of AP Stats. And we hit it again and again and again. In my first picture, what is going on is I have 500 dots in this picture. Each of those dots is a separate sample of 100 kids. So I'm going to survey 100 kids for my sample. Look at this dot right here at like 0.80. That will be a sample where I took 100 kids and 80% of them went to class. And then I would throw those kids back in and pick another sample of 100 kids. And that time, oh gosh, only 75% said yes. And then the next time I would go over here, I got 67%, et cetera, et cetera, et cetera. Each of those dots is a separate group of 100 kids. And I do that. There are 500 dots in that picture. Similarly, in my second picture right here, still each of these dots is a separate sample, but they changed it. So now this is a sample of 400 kids. So each dot is a group of 400 kids instead of 100 kids like over here. Still 500 dots, but it's a different shape to the picture when you look at it. It's different spread anyway. So let's talk about what's going on here. When your sample size gets bigger, the whole thing this slide right here is trying to emphasize, bigger sample size means less variability between samples. We've talked about the word variability already. It's just talking about how spread out things are. The data tends to be more consistent when your sample size is bigger. So let's say at the college, it's actually where 70% of kids went to class every single day. And it actually says that in the problem. 70% of kids at this school actually go to class without skipping it every single day. If I talk to 100 kids, it could be where I get a fluky sample where, wow, I got a lot of really motivated kids here. And I happen to get like 83 of them who went to school every single day. It could also be where I have a group of 100 and, oh, less than usual, I only got like 56% over here. So there's a lot more spread going on in this picture than there is over here. If you get a sample of 400, you're not going to have as many of those fluky things. Like if the answer is actually 70, getting an 85 isn't going to happen if you take a bigger sample. Because even if you get like some kids that, oh yeah, I do go to class, you also get more that don't, and it kind of balances out. So this note right here is a really important one. When your sample is bigger, your data becomes more consistent. If I take a sample of 400 and you take a sample of 400, we're probably going to get closer to the same answer. We will hit this again and again and again as we go through this class, so no worries if that's still a little shaky right now. So let's see what else we've got here. Remind myself how much more I have. All right, a couple of vocab words here. Inference is basically all of second semester of AP Stats. We're building up little pieces of it now, but we really hit this hard second semester when we talk about confidence intervals, significance testing, and so on. All inference means is using your sample to talk about the whole population, using results from a little sample to apply to the whole population. That's what inference means. When you collect results, you're not always going to get the exact answer. That's called like you may be off by a little bit just by chance. When I looked at my last slide right here, the answer was 70%, but I don't get exactly 70 every time that we do it. I could be a little higher, could be a little lower. The amount that I think I could be off by, the maximum amount, is called the margin of error. So if you look at this problem, it looks like most of my data points are within 5% of 70. Whereas over here on the second picture, you can see it's a lot more spread out. It's more like, 10% each way, or even a little higher than that. So the margin of error is lower on this picture, and all margin of error really means is the maximum amount you think your answer might be off by. And when you increase sample size, it makes your estimates more precise. We've talked about this already. It decreases variability between samples. So let's go ahead and talk about a few other things with regards to sampling. That last part right with the pictures was a little bit confusing. This isn't so bad. We want to talk about a few other things that can go wrong after you've selected or when you've decided you're going to select your sample. So, okay, I've convinced you that your sample should be random. What happens now? First one is called undercoverage. And undercoverage means that some individuals were not actually able to be chosen for your population. Okay, so some people were not able to be chosen. Classic example. There's a famous newspaper picture that you might have seen from like the 1940s. It says Dewey defeats Truman. It was for the presidential race. Dewey defeats Truman. Harry Truman is a president that you guys have probably heard of. I don't even know Dewey's first name, John maybe. Thomas, I'm not sure, whoever he is, everybody thought he was going to win. It was the night before the election and the results weren't in yet, but newspapers back then had to print earlier than they otherwise, like before the results were final. But they felt so good from their surveys that they actually went ahead and just said, oh yeah, Dewey's totally going to win, and published this headline. And it's a picture of Truman like laughing, looking at it after he actually won the election. What had happened? There were a couple of reasons, but basically one of them was they did a lot of their surveying by phone. So they called people and they said, hey, who are you going to vote for? Well, back in the 1940s, having a phone was a fancy thing. So they ended up talking to a lot more wealthy people who were in favor of Dewey, and the people who without phones, who tended to have less money, voted for Truman and pushed him over the top, and he ended up winning. That's under coverage because some people, the people without phones, weren't able to be contacted. That happens all the time. Like if you do an internet survey, some people still don't have access to the internet. So you're not going to hear as much from people in rural areas, older people as a general rule, or people who can't afford to pay for the regular internet access. So certain groups get left out if you're not careful on where your data comes from. That's called undercoverage. The next thing on here is called non-response. And non-response is when you choose your sample randomly. So you've chosen your sample, everything is cool. You contact people, hey, be in my sample, and they either say no or you can't get in touch with them. Okay, so this happens a lot. We do a semester project related to sampling, and people will like email kids like, hey, you've been chosen to be in my survey, and the kid's like, I don't want to do that, and they ignore it. That is an issue because the kids who ignore your survey may feel differently than kids who respond. So you still run the issue of bias, even though you did your sample randomly. This sounds a lot like voluntary response, which we talked about earlier in this section. The key difference is that voluntary response, you just put out a general, hey, be in my study if you want to. You didn't do anything random. So voluntary response, there was no randomness. You just let people invite themselves. Non-response occurs after you've selected your random sample. So you did the right thing and you randomly sampled, but then people didn't respond. So what would you do in that scenario in real life if that happens? Well, you try contacting them again and try to get them to follow up and be in the survey. And if they wouldn't, you could randomly pick somebody else, but you'd put like a disclaimer that this many people didn't respond because those people could actually feel differently. These two things right here and many others are examples of response bias. Response bias is a general catch-all term for things that might happen or that you might do that might influence the results or responses that you get. So response bias is as opposed to sampling bias. So your two main types of bias are response bias and sampling bias. Actually, these two things right here, I misspoke a minute ago. Those aren't really response bias. I'll give you some examples of things that are. So sampling bias is bias in how you collected your data in the first place. Response bias can happen even if your results came from a random sample. Let me give you a few quick examples. The wording on the question can lead people to respond to a certain way. So if I think everybody at MRH should take 4 years of math instead of 3, I could be like, hey, given that colleges want to see 4 years of math, and math is an essential tool for being great in life, and et cetera, do you think we should do 4 years of math instead of 3? It doesn't matter if I was actually random in who I talked to. If you can tell that I want it, you may say yes, just to agree with me, even if you don't actually believe that yourselves. So the way that you word a question can matter. We actually do our first semester project on response bias. So this is something you guys will get to practice on later on in the semester. One thing that kids did that a good project from a couple of years ago, they had a Google survey about, doesn't even really matter what, it was just a random survey. And they had the big text box option and the little text box option. And they just wanted to see if people would type more in the big text box. And they actually did. So something as simple as the size of the text box or the color that your question is written in, or even the order of the questions can influence responses. I did a little bit of that with you guys in the survey I gave you. I played around with the order of the questions and did some things that counts as response bias, which we'll investigate later on, not in this video here. One more really good example, and then I'll move on. There was a survey where basically they asked people like, how happy are you with life overall? That was like one question. They had you rate it. So how happy are you with life? And then followed it up with how many dates have you been on in the past month? And then they reversed the order of the questions and asked about the dates first and got lower responses for the happiness with life in general. So something as simple as like, what order do you ask things in can make a difference in responses. So let's close this out by talking about these couple of examples right here. Again, practicing vocabulary. If you're not ever sure on a vocab word, don't say the word guess, just describe it and that will be fine. This is not so much of a buzzword class where you have to know, oh, that's voluntary response or non-response or whatever. But let's go through these. If you choose your sample out of a telephone book, that is going to be under coverage. There are people who do not have a phone number in the book, and you won't be able to contact them as a result. So you finally get a hold of your sample, you choose your sample, but some people don't return your calls. That's non-response when they choose not to be a part of your study right there. And then if your sample is just people walking by on the sidewalk, that is a voluntary response. So those are 3 things that are all bad sampling techniques. All right, this last question, and then we're done with this video here. I'm not going to write this one, but I'm just going to talk through this. They found that 84% of people oppose banning disposable diapers, and then explain how this like leads to bias. Anytime they talk about bias, you have to do those 2 things. What's the problem, and what direction does this problem probably send things? So this person says it is estimated disposable diapers are less than 2% of the trash in landfills. In contrast, beverages are 21% of the trash. Given that it's only 2%, would it be fair to ban disposable diapers? So people are going to look at that and be like, oh, 2%, that's not very much. Those drinks are way more. So no, we shouldn't ban diapers. That's ridiculous. This question right here is very much pushing people towards the conclusion that having such a small percentage banning it isn't going to make much of a difference. So the wording of this question is very much pushing people to say that no, it's not that big of a deal. The wording suggests it's not a big deal. So people are going to say, oh, don't ban them. And they're pushed in that direction more than if they had asked the question and just innocently and neutrally. So the actual percentage of people who are in opposition, this is probably overestimating that. It's probably higher than the actual answer of people who oppose. So that would be a good way of describing the bias in that question.